Welcome everybody to this week's CBP Nonprofit Research Video Review. I'm Dr. Deed Harrison. I am President and CEO of Chiropractic Biophysics Seminars and Technique, but I'm also President of Chiropractic Biophysics Nonprofit, our Spine Research Foundation. If you look at this link at the top, this is how you can identify or find out more information about Chiropractic Biophysics Nonprofit. And if you've been enjoying these weekly video presentations, please consider supporting us directly at this link and then listening to the short message from me at the end. We've published just over 150 peer-reviewed research publications in some of the top spine journals in the world. These include chiropractic journals, physical medicine and rehabilitation journals, biomechanics journals, as well as surgical journals. So our work has been very widely and broadly received, and I believe that we've had broad impact in spine research. So what we're doing is we're going through our research publications in video format. Now, basically I'm giving you a summary of the research and I'm going through it in enough detail so you understand the project, but I still really advise you to go and read the paper if you are indeed a chiropractor interested in this line of work, or you're a researcher interested in this line of work. Obviously, if you're a patient, then certainly this video might actually be too much information, but it should stimulate interest in chiropractic biophysics technique and also clinical results, and should hopefully prompt you to go and see a CBP style chiropractor. This week what we're going to do, this is our 19th video in the series, we're going to go through our 1998 paper that was in the Journal of Orthopedic Research. Now this paper is one of our foundational papers for the lumbar lordosis. This is really our elliptical model for the sagittal plane alignment of the lumbar curve. Okay, this paper was very important. It was a high impact paper when it came out. In fact, it was one of the top papers that year in spine modeling of the lumbar curve. To my knowledge, we were one of the only groups of chiropractors to have been published in the Journal of Orthopedic Research in 1998. So let's go through this project. Can the sagittal lumbar curve be closely approximated by an elliptical geometry? My dad's PhD advisor was lead author. Then my father, Rene Caillet, Steve Tronovich, a former CBP employee, and then myself, Deed Harrison. Now, the reason my dad's PhD advisor is lead author is this is a high caliber mathematical paper. I'm not going to go through the math on elliptical modeling, but I want you to know the math involved in taking what's called an inverse of an infinite series of elliptical tangent lines to calculate segmental angles to the that are tangent to the lumbar curve. That math had never been done before. My dad's advisor, PhD in mathematics, formerly at the University of Alabama in Huntsville, he had to develop original mathematics for this project, okay? So this would have qualified for a PhD dissertation. This is how complex this particular project is. So personally, I don't have a PhD in mathematics, so I'm not gonna go through the math. But if you really wanna see it, get the paper and you can read through it and your eyes will probably gloss over. What's normal? What is supposed to be the geometry of the lumbar spine? Very important question. You can't judge a patient, their health and well-being, versus a disease condition without having a benchmark normal to gauge them against. Okay, so there's background work that has to be done here. You'll see. Number one, we had to study the reliability of our line drawings. We already went through that in the earlier videos, but I'll summarize that quickly with a slide. So we had to have a line drawing method and we had to establish the reliability of that. Then what we have to do is we had to take a normal group of healthy individuals and we have to look at their X-ray alignment features on their lateral lumbar curve. We did that in a previous project. Now what we can do is we can look at that data and we can develop a quantitative model that best fits that data. So even though we call it an idealized model, it's an idealized model that best represents the average subject's anatomy, assuming that our average subject population is a healthy population. So what's normal? Big question, but very important question. You cannot say that somebody is abnormal until you have something to gauge it against, right? That's everything in healthcare. No matter what you're doing, you're comparing it to a benchmark normative data set. Your heart rate, your blood pressure, your respiration rate, your red blood cell count, your white blood cell count. You get the idea. All on and on and on. Your testosterone level, your estrogen or progesterone levels if you're females. All these things, you have to have an established normal to judge a patient against. It's no different when we look at the lumbar x-ray from the side view to say, hey, you're within normal limits, this is what your low back curve should look like, or you're outside of normal limits. So our lines, we have to do segmental and total angles of curvature analysis. We call these relative rotation angles, or RRAs, and absolute rotation angle, or ARA. ARA is the total angle, RRA is the segmental contributions to the curve. So just a quick review, we do these lines, posterior body lines, T12 versus L1, that's my T12 to L1 RRA. L1 back of the body relative to L2 back of the body, that's the L1, L2 RRA, and so on. We go all the way down until we get to L5, S1. And then we'll measure the sacral base angle as the sacral base to horizontal. The last line we're interested in is the translation distance, okay? For our elliptical model, we're not so interested in that translation distance of T12 relative to a vertical line at S1. We're interested in the segmental contribution to the curve and the total angle of curvature. So what we did is we took our 50 consecutive but retrospectively analyzed normal subjects. These subjects were free from back pain, history of back pain, they were free from degenerative joint disease at any level, they were free from congenital anomalies, blocked vertebra, and they did not absolutely have, obviously surgery. Okay, so this is our normative data set, right? Okay, so then we look at their x-rays and we look at their segmental angles, and then we have to construct a model. Okay, now our model, what we're going to do is we have to break the lumbar spine down into its components. Okay, it's bony, rigid components, and then it's flexible, interlinking component, which is the intervertebral disc. So when we look at the sagittal view or the side view of the lumbar curve, we're going to say that the lumbar curve goes from the inferior body corner of T12. T12 is the bottom of the thoracic spine, and it transitions into the lumbar spine. So we're going to say the inferior body corner of T12 all the way down to the top of the sacral base. So we're going to use posterior superior of S1, that's this point right here, all the way to the posterior inferior of T12. That's going to be where we're going to say that's our elliptical model, the top and the bottom. You have to have a starting and a stopping point, okay? Now, we've taken this lumbar curve from upright and we've turned it on its side. The reason is it's easier to work with mathematically when we talk about modeling. Okay, so we're going to build quadrants. You remember in algebra you had a quadrant, first quadrant, second quadrant, third quadrant, fourth quadrant. Well, we're going to try to fit this lumbar spine into the first quadrant because the numbers are easier to work with, right? You kind of remember things, y is positive up and x is positive to the right. Well, my first quadrant, all the numbers are positive. It makes it easier to work with. And then we're going to, build this model assuming the vertebra and the disc have certain ratios relative to each other. So based on our normal subjects, and I'll show you a table of this, we broke the vertebra down, the body of the vertebra, into 4 pieces. Okay, so the back of the body of L1, we're going to have 4 pieces, or we're going to have quarters. Okay, then the disc is going to be worth 1/4 of the size of the vertebral body. Okay, so my T12 to L1 disc is 25% the total height relative to the L1 vertebra. The L1, L2 vertebra, or disc, is 25% the height of the L2 vertebral body. Okay, so we base this on studies in the literature as well as our normal subjects. This is how we acquired this data. So the disc height is 25% of the height of the vertebral body on the posterior aspect. So I have 1, 2, 3, 4, 5 vertebra. Okay, so I have 5 vertebra, and each piece is worth a quarter, or I would say, 1 out of 4. So I can say 5 times 4 is 20. Okay, so take the number 20, and then I have 1, 2, 3, 4, 5, 6 discs. Okay, so then I have 6 pieces of a disc. So then I have 20 plus 6, I got 26, so my total is 26 pieces. And so if you look at how we're scaling this and breaking it down, the T12 to L1 disc, that's 1/26. The L1 vertebral body is 4/26, so you add that to the first one, I get 5/26. And then I add the disc, I get 6/26. And I add the vertebra, I get 10/26. So we're just breaking things down into its piece components so we can be able to calculate these segmental angles or our relative rotation angles. So we've built a model. We've said the vertebra relative to the disc. The vertebra is 4 times the size of the disc in its height. That's what we've done here. Now, what we're going to do is we're going to take a sonic digitizer. Sonic means sound. So I have a digitization system. I touch a point on an X-ray. The computer then reads the two-dimensional coordinates of that point, and it inputs it into a computer system. So I can look at the relative points of this entire spine in the discs, and then what I can do is I can take that data and I can see if I can pass a certain curvature through those points. So shown here, these diamonds would be points on the spine. So let's say this is L1 vertebra at the bottom, and this is L1 vertebra at the top along the posterior aspect of the vertebral body. What I can do then, I have those points, I can see how well I can fit a certain geometry through those points. Okay, so if I take an example here, I've taken what looks like a piece of an ellipse. This would be almost one quadrant or 1/4 of an ellipse. So if you took an egg and drew it as an oval, I'm looking at the upper corner or quadrant of this oval. And I'm showing it here on this model. And then here's points on the X-ray, each one of these diamonds. I pass a curve through it, and then what I do is I look for how far these points that I've touched with my sonic digitizer are from my best fit curve model. Okay, so the distance here between the diamond and the curve, we'll call that DI. Okay, what we do in curve fitting, it's a type of modeling, is we take those distances, we square them. Okay, so I take the distance and then I square it, and then what you do is you add up all the squares, and then I find the curve that has what's called the sum of the least squares error. Okay, so it's a type of mathematical modeling, and we look at a close approximation of the model relative to the points on the lumbar spine. So least squares error. Now you get the idea of what we're doing. So if I have a model that has 10 millimeters error per point and I square it, now I get 100 millimeters, then I sum up all those, I'm going to have a very large error. That means I didn't really fit this structure very well at all. My model is not good. It's way off. You wouldn't want to accept that. But if I have a model that is a close approximation to how accurate I can touch points on the vertebra, let's say I'm within a millimeter or 1.5 millimeters with my sum of my least squares error, that means that I'm within the accuracy of my ability to touch points on this X-ray with my digitization system. What that means is that's a highly accurate model. Okay, so this is what we've done. So we took our subjects, we took their coordinates, we put them into a computer program, we rotate it to where it fits in the first quadrant, and then here we go. Here, this point right here is the inferior body of T12. Here's the T12 L1 disc. Here's the back of the body of L1. Here's the back of the body of L2. And all the way down to the top posterior superior corner of S1. We then pass a geometric shape in the form of an ellipse through all those points, and then we evaluate them with the least squares error. Here's what we find. The average error is 1.2 millimeters. Okay? That's an extremely small least squares error approach when you add all those up. That's actually within or at the limit of my ability to touch points on this digitization system that we have. So we're within the ability to actually make the measurement with our modeling approach. This is highly accurate. What we identified is the lumbar lordosis, or the lumbar curve from the side, can absolutely be approximated by this piece of an ellipse. Now shown here, it looks like we're off a little bit, but that's blown up. The scale is not right. What you have to look at is the average error, 1.2 millimeters, okay, per point. Now, we build a height over length ratio so we can see what the curve is relative to what's called the Delmas index. The Delmas index was a model that was established back in the 1950s and 60s. Delmas said the spine should have a height over length ratio of 95% as ideal, with a range of 94 to 96%. It was a proposition. There was no real validity in the Delmas index at that time. The methods weren't sophisticated enough to really, truly say, hey, do subjects actually fit this? So we put this height over length index in there to show that we're actually at the upper end of the Delmas index. So he wasn't too far off for the 1950s and 60s compared to what we've identified. Okay, so here's our elliptical model, or the piece of the ellipse. You can see that this is one quadrant. And in fact, it's 83.7 degrees of a 90-degree quadrant, right? So we're almost fitting an entire quadrant if I, break it down into 90, 90, 90, and I have a 360-degree total graph, okay? Now, to give you a little bit better perspective, when we did this model, there's different ways to control for variables. You can allow the computer to select where the short axis of the ellipse versus the long axis of the ellipse passes through. That's very cumbersome. The computer will sit there and go, through 1,000 iterations. Or what you can do is you can force a best fit approximation of one of these axes, and then you can calculate the other ones relative to it. Of interest, what we identified is when we allowed the computer to select itself versus when we self-selected, we forced it, we came up with similar results. So here's what we identified. In an ellipse is an oval. I have a long axis and I have a short axis, okay? I can make a ratio of those two. We'll call the short axis B, that's what they call it. The long axis is A, okay? So if I go B divided by A, I'm going to always be less than 1 because the short axis is shorter than the long axis. In a circle, those two axes are identical. It's called a radius. So A and B are identical. They equal 1. It's a radius. So a circle is a special ellipse where B over A equals 1. Now, an ellipse, I can qualitatively and quantitatively define my ellipse by the ratio between B divided by A. But what we have to do here is we have to look at where these axes pass through. Of interest, the semi-minor axis that we call B passes through the inferior end plate of T12. So this is my short axis of the ellipse. We call it B, the semi-minor axis, okay? So the inferior body of T12, inferior end plate, of interest, that's where our elliptical short axis passes through. So it defines the coordinate start point of this ellipse. Okay, then we have my long axis called the semi-major axis. Okay, that's my A. A is parallel to the posterior body of T12. Okay, it very nicely fits that way, of interest. So the major axis of the ellipse is parallel to the body of T12. The minor axis is absolutely along, parallel to and right along the inferior end plate of T12. Okay, and then this point where the two cross, the geometric center of the ellipse, if you will, that's a very important point to control for as well in terms of defining the way my ellipse lines up in space. Okay, so what we've done is we've taken this, defined our elliptical model, and then we pass the ellipse through these points here. And we found a least squares error 1.2 millimeters per point or less. Okay, so this gives you perspective into the ellipse. Now the model looks like this. So it's nice to have a series of pictures that now explain or depict what I've just explained. So A is my major axis. It's parallel to the back of the body of T12. B is my minor axis, and it goes right through the inferior end plate of T12. Okay, and you can see where these points cross in space. That'd be the geometric center of my ellipse. We can define that in a Cartesian coordinate system. Okay, and then here's my elliptical model, inferior body corner of T12 down to the top of S1. Now what we have to do, this is where the math really comes into play. We have to calculate the segmental angles along this ellipse. We have to take the tangent to that curve at that point. That's where the high mathematics come in. That had never been done before, believe it or not. It had never been done before in mathematics. Nobody ever took an elliptical model and said, well, let me calculate tangent lines and derive segmental angles along that model. Nobody did that. Crazy, but nobody did it. Okay? We'll look at what the results of that were in a second. Now, part of our project, we had to look at this and go, well, our normal subjects are over here. And what this is the ratio of the height of the vertebra relative to the height of the disc at every level. So this is L1 vertebral body height, this is L1, L2 disc height, okay? And then we get a ratio. So we go all the way down, here's the data from our study. 3.9, 3.8, 3.5, 3.6, and then my funky Windows operation arrow that covers it. I can't see it. I apologize, but I don't know right now how to get that damn thing off. If anybody does, you know, log on to this or write a message on YouTube and tell me how to get that little symbol off, because I can't get it off just yet. Anyway, the L5S1 body to disc ratio isn't shown. Now, we took this data and we rounded up. We said, let's make it easy, 25%, the ratio. You can see it's not identical, right? So it's not identical. And then we looked at other studies in the literature. Gilad and Nissan. This was out of the Journal of Anatomy. And they reported disc to body ratios in anatomic specimens. You can see their ratio, 4.2, 4.2, 3.9, 3.5, 3.4. So it looks like the ratio is, you know, the disc is a little smaller at the top compared to the height of the vertebral body, so the ratio is bigger overall, and then it tapers down. So the discs look like, in these two different populations, it looks like the disc gets bigger relative to the body as we go down. Our model, we didn't account for that. We made it easy. We just said, let's use 25% because it's easier to work with. The problem is, will these variations in disc to body height in the anatomy, will that affect our model? Right? That's an important question. So part of this, we had to, you know, program this into the model to see, will this affect the output of our segmental angles? If it does, now we have a challenge, because now I have to take every individual person and I have to normalize their disc and body height ratio to them and then readjust my model for them. So that would add an extra level of what we would call chaos. We would have to do it though as a clinician. It would be the right thing to do. So the first step is, do we even need to? And we cross our fingers, we go, let's hope to God we don't need to, because this would suck, right? It would add extra work to every case that came in. We'd have to have a computer model that said, well, your disc to body ratio isn't 25%, it's, you know, 3.1. And, you know, then we'd have to recalibrate, recalculate, and come up with a normative data set for you. And of course, you would say, yeah, I need you to do that. But the first step is, do we even need to do it? So what we did here in the table 3 in this particular paper is we took different data out of the literature and we rebuilt or reanalyzed our elliptical model with the equations to predict the segmental angles, and we said, well, let's see if it affects things. So NS means our normal subjects, okay? Our normal subjects. Kolwicki et al., that's a study out of the literature in spine. Gilad and Nissan, that's our anatomy, you know, the anatomy paper that I just showed you. And then here is a uniform model. So here's a uniform model, and what that means is our 25% disc to body ratio. And then here's some of our digitized subjects. Okay, so this is what we digitized in 50 subjects. And then we look and we calculate our elliptical model segmental angles, and we see at T12L1, do variations in the height of the disc to body change the numbers? 2.7 degrees to 2.9 degrees, 3.6 degrees. We're within a degree. It doesn't matter. That's within the ability to make the measurement. Here's one, 4.1 to 6, 5.1, 5.1, 5.3. The only outlier is this 4.1, right? And this is segmental angles from normal subjects in the literature. So this is not really looking at do variations in anatomy affect this. This is actual data from the literature on looking at the segmental angles in normal subjects. So these ones here, these are more relevant. You can see within the model limitations, if you change anatomy, you don't see a big change in the model output. Okay, so we go all the way down. We look at these numbers here. They're all within a degree, within a half a degree of each other. So our conclusion was variations in the anatomy, disc height to body height ratios do not affect the segmental outcomes of our elliptical model when you put it through and make it calculate it. Compared to normal subjects that we've measured, it's a very close approximation. Okay, so this is a normative data set, and these are modeling interpretive studies. Moral of the story is this. If I look at the average value in the asymptomatic population, looking at a data set that we did previously in 1997 versus our idealized model that was constructed off these subjects' anatomy, our elliptical model, you can see a very close fit of X-ray data to modeling data, right? So a model is only useful if it can predict or come close to what you see in actual reality. So that, what we've done is what's called an exploratory versus a confirmatory approach in modeling, okay? So we build a model, we base it on some subject data, but the model itself is not 100% based on the subject data. It's an approximation of that subject data using what we call optimized trends, if you will, the 25% disc to body ratio. And you can see it's a close approximation. Why would we want to use the model instead of average data? Well, there's no such thing as a perfectly normal sample, right? People reserve the right to be screwed up. So you either increase the sample size to thousands of subjects, or what you do is you construct a model that approximates what we see, and then you use that model if it fits. It basically smooths out problems in people is what it does. If you don't like that, too bad. That's what mathematicians and engineers do. They build models of things and then use the models. That way they smooth data sets out. Obviously, extreme alterations in anatomy we're going to have to adjust for and account for because they won't be fit by the model. However, in most cases, we're going to use the model instead, especially when we start to do investigations on how this certain changes in the lumbar curve affect people, right? So we'd like to use the modeling data instead of just a subject's spine, right? So our model closely approximates what we identify in 50 normal subjects. At this time, when this paper came out, it was the most, what we would call, simple yet profound model of the lumbar lordotic curvature. There were other models, but they were quite cumbersome in their approach. They required, complex polynomial functions and such. This was a very simplified model as a geometric shape that people could qualitatively wrap their heads around, and also that we could calculate these segmental angles. Nobody had done that before. Okay, so previous models, these polynomial functions, nobody calculated the segmental angles based on those idealized polynomial functions. We were the first ones to take this model and actually calculate the ellipse. And you can see why maybe previous authors didn't report the actual segmental angles relative to the model. It's because the math wasn't around, and it would take a very, very savvy, a very brilliant mathematician to develop new mathematics. I mean, you got to consider this. This is specialized, math. It's rare that somebody originates and develops new mathematics, if you get the point. And that's what this paper actually has in it. So, our conclusion summary. An elliptical model could closely approximate the lumbar lordotic curve of normal subjects. Also, our model was not affected by variations in subject anatomy relative to changes in the vertebral body and disc height ratios that were found in the literature. It was a close approximation, so using the 25% ratio in our model is justified. Our model provides a missing rigorous initial starting position for the lateral lumbar curve for normal healthy subjects. This model can be used to test a variety of things. Number one, do people with different pain syndromes have a different model relative to our normal subjects that we've just modeled, right? Or developed the model from, okay? So is there going to be a difference from people with a condition relative to this model? These are future projects. Is there a difference in health status in subjects that have a healthy elliptical model versus subjects that have poor health? That's different than pain, right? We're talking about true, health disorders, not just I have back pain, right? Is there functional differences between people that have alterations in their elliptical model? Function means, do they walk different? Do they have different movement patterns, range of motion? Do they have different flexibility, etc.? Are they more predisposed to injury because the stresses, loads, and strains, deformations are different in these spine tissues? And then are they more predisposed to injury when I apply load? So if somebody has an impact load or a lifting load, is there more chance of having injury to the system with alterations in the ellipse? These are all future projects that we talked about or proposed that this model could be useful for. Okay, so that's our summary, our conclusion. Hopefully you've enjoyed that. That's one of our benchmark studies. The foundation of some of the CBP work is you have to have a model, a normal starting position to judge somebody against. Okay, somebody comes in with a condition, or maybe they don't have any condition yet, right? Maybe they're asymptomatic and they think they're fine. Well, part of what we do as healthcare providers is we've got to look at risk factors. Does this person have a risk factor for developing a condition in the future? Or do they have a problem now that is correlated to the condition that they come in with? This is a benchmark foundational study for us. This is our optimized lateral lumbar curve. We've modeled it with an ellipse, and we've developed segmental angles that the clinician can use to compare a person to or compare them against. Hopefully you've enjoyed this presentation. If you have, please consider listening to the following message and consider supporting us. Until next week, thank you very much for your time and attention. If you like this information, if you're a patient, you need to go to a chiropractic biophysics trained chiropractor. You can find us all over the United States, Canada, and international locations. Go to www.cbppatient.com and look up CBP providers in your area. It's an easy to use, user-friendly site. Search for, at first, a general or advanced trained CBP chiropractor. If you can't find one of those, then find somebody that's at least on the directory and has taken our courses and that does the work, okay? So let's go to a CBP trained chiropractor, www.cbppatient.com. If you're a chiropractor and you're interested in this, either learning more about it or maybe it's brand new to you and this particular video research project intrigues you, come to our website for doctors. Go to idealspine.com. We've got a lot of things there for you. We've got training, we've got conferences, we've got products. Love to have you on board and become one of the CBP doctor family providers, right? We need your help. There's patients out there that need you, and if you don't get trained in this work, then you're not going to be able to provide them the type of service that we think you should be providing them from a corrective care point of view. Also, lastly, anybody out there, we also need your help to continue to do research investigations like this, right? These are time and dollar consuming projects. If you will, go to our website directly and sponsor and support Chiropractic Biophysics Nonprofit. Make a donation of any amount to us. Also, you can do it indirectly on Amazon Smile. Just select Chiropractic Biophysics as your nonprofit foundation, and when you purchase through Amazon Smile in Amazon, CBP Nonprofit will get 0.5% of all your purchases, which is a big deal at ADSLA.